So hello everyone and welcome to another webinar from CES. I hope you are all doing well, whether you're working from home or office. My name is Hassan Rahhal and today I will be talking to you about pragmatic digital transformation. A few notes before we start, a kind reminder to keep mics off during the presentation. If you have any questions, please post it in the chat. We have our AEs available to help you with your questions, and we can try to tackle them as well during the question and answer sections. So digital transformation is a term we are starting to hear daily, and it is becoming a major trend in the industry. This is one of the reasons we wanted to tackle this subject. Throughout our engagements with companies in the region, we often hear and feel the challenges and obstacles that they face when they try to follow this trend. In this presentation, I will try to highlight some of the common obstacles that typically slow down companies and investigate possible solutions for these obstacles. We will also try to examine this trend from different aspects and try to address the questions and concerns that different personas face, whether they are engineers, scientists, project managers, or IT and system architects. While preparing this presentation, I thought the ideal way to start is by giving a definition of digital transformation. Naturally, I tried to look online for definitions of the term, and I noticed something interesting. It seems that the definition of digital transformation changes from company to company according to their line of business. A company like Salesforce, for example, defines digital transformation as the reimagining of sales, marketing, and customer support relationships. An automotive company, on the other hand, defines digital transformation as the incorporation of digital technologies into their new car models. The first impression that I had was that, like agility, digital transformation is one of these terms that means different things to different people and are at risk of becoming meaningless. However, if you think about it from a different perspective, it makes sense that such terms cannot remain rigid and have to adapt to the domains where they are applied. If we want to put a generic definition that captures the essence of digital transformation, we can think of something along the lines of how CIO magazine defines digital transformation. It marks a rethinking of how an organization uses technology, people, and processes in pursuit of new business models. It is a process of rethinking in a dynamic world where needs and expectations vary on a daily basis. Take a simple example like the doorbell. For hundreds of years, the doorbell underwent multiple changes in the mechanisms and design, but the operation itself remained unchanged. A doorbell, as the name implies, rings a bell. The change in customer needs and expectations in the 21st century is what drove a fundamental change in the doorbell. More features such as video cameras, smartphone interfaces, and security features became things that customers were interested in or even demanded. When we look at systems like the modern doorbell, we sometimes forget about many of the underlying technologies that enables its operation. We cannot have a modern doorbell without computer vision, signal processing, and embedded systems, all of which are fundamental engineering concepts. Incorporating these technologies into modern day systems is not an easy challenge, and companies often have to undergo significant changes to do so. And this is one of the main objectives of the presentation today, to help show how what we consider to be the key changes that companies need to undergo to be able to achieve digital transformation. In the last few years, the need of such transformation has been increasing exponentially, with companies spending billions of dollars on acquiring companies, technologies, and intellectual property that can help them enhance their digital transformation efforts. You might be surprised that like a company like Amazon acquired Doorbell, the Ring company, which we saw in the previous slide, for more than $1 billion. You might have also heard of similar acquisitions, like when Google bought Next for more than $3 billion, or when Microsoft splashed around $20 billion on a Nuance, an AI-based technology company. Almost all large companies currently have an internal roadmap for digital transformation, and it will not be surprising to see such acquisitions on a regular basis. We work with many customers and companies across different industries, and the definition of digital transformation changes significantly from one to the other. However, as we mentioned, the essence remains very similar. In this slide, we try to highlight some of the trends and application areas which companies in different industries strive to adopt and which are heavily linked to digital transformation. Topics like autonomous systems, automated driving fundamentally rely on digital technologies and are often painted in the same picture as digital transformation. Predictive maintenance is perhaps one of the most trendy terms across all industries, and the majority of companies link it to their digital transformation efforts. The same can be said of various other trends such as AI-powered consumer goods, smart wearable devices, and AI-powered finance. All over the world, companies try to incorporate digital transformation into their vision and internal processes. And through our global and local engagements, we have seen two major trends in the market. Many companies opt for a proof of concept approach, hoping that a positive outcome can be extended to the organization level, while others opt for a bottom-down approach with a complete overhauling of their processes and systems. We often see both approaches struggle, one because of the inability to scale up, and the other because of the inability to incorporate well into the lower stages of development. In the following slide, we will investigate some of the reasons that make such approaches difficult or even impossible to implement. To understand why organizations struggle with these two approaches, we need to look at the three key components within an organization: processes, people, and technologies. The people component encompasses the profiles, experiences, and skill sets of employees within the company. The processes component covers the internal policies and systems within the company, while the technologies component includes the accepted platform, systems, and tools within it. Any attempt for change that doesn't take these three components into consideration is doomed to fail. Companies adopting both the proof of concept and the platform and infrastructure overhauling approaches run into multiple challenges due to the unreasonable expectations that they set to their people and employees. This happens as well due to the need for new skill sets or because of the static roles of its internal setups. They also face challenges due to the stagnant internal policies and systems or the lack of visibility of what needs to be changed and what has to be kept the same from the old processes. Some challenges are also due to the lack of suitable technologies or systems within the company or the incompatibility of these technologies with the new setups. We believe that the best way to achieve digital transformation at a company is by adopting a hybrid model that mitigates the risks of the two previous approaches. This system is what we call pragmatic digital transformation. We define pragmatic digital transformation as the systematic use of data and models to create and deliver superior value to customers throughout the entire life cycle. Pragmatic digital transformation does not require starting from the ground up or completely overhauling entire processes and assets. Its fundamental principle is reuse. In pragmatic digital transformation, data, models, and team skills are applied systematically to workflow through the life cycle of the product or service. This is achieved through the adoption of model-based design and model-based system engineering. The systematic use of data can start with analytics developed specifically to get insights from experimental and research data. This is what we refer to as real-world artificial intelligence. It also means scaling and extending those analytics to huge sets of live and archived data acquired from manufacturing, maintenance, and other business processes to enable data-driven decisions not only during research and design, but also in production, operations, and maintenance. Finally, it involves agile workflows that are designed to speed up development and delivery. In the next slides, we will discuss each of these pillars in details. In reality, each of these sections can have a specific seminar designed to talk about a different aspect and workflows. But in this presentation, we will try to touch from high level all the aspects of these different pillars. We will start with the first pillar, which is the adoption of model-based design and model-based system engineering. Today, systems are very, very complex. A modern car, for example, includes numerous technologies seamlessly working together in tandem. In reality, getting these technologies to coexist, not alone to cooperate, is a huge engineering challenge. Each of these components and technologies requires specific domain experience and is usually developed by a different team or group of teams. Model-based design provides a framework to facilitate the integration of these components through the systematic use of models throughout the development process. In today's engineering, a company needs to adopt model-based design as a first step in the road towards digital transformation. It is almost impossible for companies to manage the complexity of today's systems without a model-based design framework in place. Model-based design allows engineers from different work groups and different disciplines to work together by developing the various components of a complex system and simulating the integration between these systems. MATLAB and Simulink provide an ideal platform to implement model-based design. In this example, you can see a Simulink model of a transmission system. The model we see here includes a mechanical subsystem, which is designed using physical mechanical components, a control subsystem designed using state flow logic, and the dynamics of the vehicle built using Simulink blocks. This work usually involves 3 different groups of engineers from different disciplines, simulating their work in one unified platform. Model-based system engineering, on the other hand, brings model-based design to system engineers, architects, and other engineering groups, and ensure that items across the architecture and design worlds stay in sync. System engineers can establish digital threads to navigate between system requirements, architecture models, implementation models, and embedded software. Model-based system engineering facilitates collaboration between system architects, design engineers, software engineers, and test engineers by providing a uniform development environment. System engineers can build and design high-level abstract designs according to the project requirements. Design engineers can then model the individual subsystems according to these requirements and simulate them. Software engineers can then generate standard compliant code from these subsystems and automatically map them to the different requirements. Throughout the process, test engineers can perform verification and validation on each stage of the development, whether it is the architecture level, the modeling and simulation level, or the generated code level. This is in essence what model-based design and model-based system engineering is about. It allows you to use a unique unified platform in order to simulate your entire system from architecture to model to actual software implementation. The second of the pillars of digital transformation is the use of real-world artificial intelligence. In this terminology, real-world is as important as essential as the word artificial intelligence. AI needs to be integrated with a multitude of existing systems and subsystems, and finding a way to do that is essential in the efforts of digital transformation. Let's start by looking into the specifics of an AI workflow. The workflow can be broken down into four main stages. Data preparation, where the access, cleansing, and other preparation activities are done. AI modeling, where the development of machine learning and deep learning algorithms and their optimization happens. Simulation and testing, where the AI subsystem is integrated into more complex systems. And ultimately, deployment into the field, whether it is an embedded device or an enterprise system. In this section, I will focus mostly on the first three portions of this deployment of this process, while the deployment section will be treated in a following part. Implementing an AI system is not something easy and is a challenging effort. These challenges come across the multiple stages of the workflow, from data preparation to deployment. These challenges can sometimes form an obstacle that prevents us from properly integrating an AI application into real-world systems and cause them to remain in the research domain. In the next slides, we will go through these multiple challenges that face engineers and scientists in each stage of the AI workflow, and we will try to highlight how these challenges are addressed within the MATLAB and Simulink environment. Starting with data preparation and management turns out to be one of the most critical ingredients to success, and it is really, really hard. Today, data comes from multiple sources, from sensors and databases. They can be structured or unstructured. They can span time with different time intervals. Data can be noisy, and it can come from different domains. The data needs to be prepared for the next stage, the algorithm and modeling stage, and this is time consuming. MATLAB helps you access data from different forms and types from different sources and bring them into a single environment. To have an idea about how this is reflected in real life, we hear in this article from Train AI a testimonial from Andrei Karpathy, director of AI at Tesla. Andrei states while he was doing his PhD work at Stanford, he did not need to spend much time on the data. He was doing research and focused almost exclusively on creating new AI algorithms. But as director of AI at Tesla, he spends 3/4 of his time on the data itself, because now he's building a car, not a better performing predictor. You may find that you end up in the same situation, spending an enormous amount of time inside the data. MATLAB and Simulink can make that time more effective and more productive. For example, most data needs labeling and pre-processing. It needs synchronization between disparate time series. It needs filtering because of the inherent noise in the signal. Sometimes we have videos that require auto labeling as well. All of this can be time consuming and error prone. MATLAB provides different data labeling apps that enable you to label signals and for analysis and for use in machine learning and deep learning applications. This, combined with other data pre-processing apps and capabilities, allow you to save enormous time and effort when it comes to data preparation. Looking at the data as just data is usually not enough. Most of the time, data sets we are working with are signals or images that need to be analyzed and interpreted as such, and not just as arrays and matrices of numbers. As engineers, we know that when looking at a signal, it is sometimes much more useful to look at the frequency domain rather than the time domain, since this is where we can find interesting features like operating frequency and harmonics, which can be instrumental for our analysis. The same applies for images, where we sometimes need to look at specific regions of interest or to focus on specific features in the image. MATLAB brings these domain tools to the user through toolboxes like Signal Processing Toolbox and Image Processing Toolbox, which allow you to have better understanding of your data sets in their physical domain. Once you have finished your data pre-processing and preparation, the next step is to move towards AI modeling. This second step of the workflow is perhaps the one which gets the most attention. This is where all the AI-based algorithms and models are built and optimized. Within the MATLAB environment, you have direct access to common algorithms used for classification and prediction, from regression to deep networks and clustering. You can also use pre-built models developed by the broader community, such as ResNet for classification or YOLO for object recognition. Sometimes algorithms and pre-built models are not enough. This is where examples come in handy. Examples are the way engineers learn how to use algorithms and find the best approach for their specific problem. We provide tons of examples within MATLAB itself that cover different applications such as deep learning models from different and object detection, semantic segmentation, as well as signal and speech processing and more. Apps often come handy in the AI modeling as well. This is a very unique strength of MATLAB. Apps like Deep Network Designer help you automate the training steps and provide visualization for understanding and editing deep networks in an interactive environment without the need to write code manually. Once you have designed your deep learning network and simulated it and tested it, you can simply generate code or a function that you include in the rest of your code. Within such apps, you can access pre-trained models, you can visualize and import models, create models from scratch, analyze them, train them, and export them to MATLAB or to code. Apps like Experiments Manager also allow you to optimize AI training by exploring hyperparameters, monitoring the training progress, defining experiments with MATLAB code, and keeping track of your work before exporting results. So how does this all fit together? In this example, we will see how we can build a classification model to classify faults of a real-world pump. We have labeled data coming from real-world machines, as well as simulated data generated using a digital twin of the device. We are using an app called Diagnostic Feature Designer. This is one of the amazing apps in MATLAB, and when you see this video, you will understand why. In this video, we have two sets of data, flow and pressure. Using this app, you can take these signals and automatically extract features, which can be generic statistical features such as means and standard deviation, or signal related features. You can then monitor and see these features and see how they affect and relate to the different faults that you have labeled from your machine. We mentioned that sometimes it's not enough to look at a signal in the time domain only. So in this app, you can also estimate the spectral image of your signal and then extract features related to the frequency domain. This all happens by doing some configurations, clicking a button, and then the app itself will automatically extract the different frequential features of these or spectral features of this signal. Now we have both the time and frequency domain signal features. We can rank these features according to their importance and their effect and contribution in the classification problem. Once these features are ranked, we can simply click on export and export these directly to another app, which is the classification learner. We can select which features we would like to export, choosing the features which are more relevant to our problem. In this app, we can look at these different features, see how they are correlated, and then we can test one or multiple algorithms at the same time. In this example, we are training 6 different ensemble methods in order to see the difference in the accuracy of the prediction. Once we are satisfied with the result, we can click on export the model to take it to MATLAB or generate a function that we can then include in the different parts of our code. You can see how using such an app can make the process much more easier than going down to MATLAB and writing the code step by step. Once you have generated the code, you can optimize it and embed it into the rest of your scripts. Sometimes training your model, your AI model, takes a lot of time. And this is where acceleration options come in handy. Within MATLAB, you can use GPUs, clouds, as well as data center resources in order to scale up your training and make it faster. The point is that a single model in MATLAB can be moved to the appropriate compute platform, saving an enormous amount of development time and allowing you to leverage the right computing technology to accelerate training. AI models have to be incorporated into a larger system to be useful. Consider automated driving. There is a lot of algorithms working around perception systems. Designing perception algorithms that can collect data from multiple sensors and fuse those data into an understanding of what surrounds the vehicle. But for these algorithms to be effective, they have to integrate with algorithms for localization, path planning, environment management, and general control algorithms, all working together to make sure the vehicle works in the way that you want it to work. This can be accomplished with an overall system simulation that handles not just the perception algorithm, but the entire vehicle itself. Other vehicles can be also simulated in the same environment to see how these different objects interact with each other. You can also test things like different driving scenarios, multiple weathers, and environmental conditions. AI handled through simulation based in MATLAB and Simulink. Simulation can also help when we have lack of data. This is where we can combine AI with model-based design to solve a problem which we face a lot of the industry. We come across a lot of customers who complain that they don't have enough data or they are not able to find enough full data to train their models. As we mentioned previously, model-based design allows you to model and simulate your system and subsystem across multiple domains. You can use these models to generate data that can be used for the AI training. This is what is now being referred to as digital twin, another term heavily linked with digital transformation. In this example, Baker Hughes built a model of a three-way pump and used Simulink to simulate what might happen during a failure. The model itself is built using physical components down to the lowest level. And in this example, we can tweak and change settings of this pump to simulate a specific fault. For example, we can block an inlet and then run the simulation. Once we run the simulation, we will know how a fault resulting from a blocked inlet will look like. We can record this fault data and use this data as an input to the AI training model to tell the model that now you have a specific data linked to this specific fault. We can do the same with multiple faults in order to generate simulated fault data and use it for the training of our AI model. We have seen multiple challenges related to the implementation of AI systems, from the data diversity, the lack of domain tools, the time needed to train different models, as well as the optimization and the different iteration it needs to build such a algorithm. MATLAB helps you solve these different issues by providing you with extensive data support, high quality libraries that fit directly with domain tools, interactive apps that help you build your models and train them in a time efficient manner, as well as the ability to integrate best practices and flexible architectures throughout your model. This is one reason that for the last 3 years, MathWorks has been named as a leader and the peer insight customer choice for data science and machine learning platforms by Gartner magazine, one of the leading scientific journals focusing on data science and machine learning. When we looked at the AI workflow, we had 4 different components, and we mentioned that the last component is related to the deployment option. In this section, we will focus specifically on this part, and this is what we call flexible compute and data topology. This section focuses mainly on the challenges that organizations face when it comes to deciding where the computing happens and where the data should reside. The best way to approach this topic is by looking at a simplified schematic of an industrial or an engineering process. In such systems, there are many places where the computing and data storage can take place, from the smart assets to the IT system. And this is where we can see the importance of having a flexible topology for data, from collection to storage to computation. So how do we decide which data topology to use? If we have a need for a hard real-time control, we should move the data closer to the smart assets. On this level, the scope of data is usually minimal due to the limitations on the microcontrollers and FPGAs that are deployed on the field. Therefore, the computation on this level is usually reserved for essential and time-critical tasks. If we are looking to make softer real-time decisions, deployment on edge systems is usually the ideal solution. These devices usually use C and C++ language and support larger data and computational scope than the hard real-time devices that we saw on the smart assets. Business decisions and time-sensitive needs are usually moved to the OT infrastructure. And this is where tools like Kinesis, Kafka, and Event Hub come into the picture. Regardless of all of the above, we eventually need to store all what we collect. All the data from operations, maintenance, and logs have to be recorded in order to use it for future analysis, for record keeping, and also to train AI models. Common platforms at this level include Hadoop, Spark, and many others. Having a unified platform that is able to handle all of these data topologies is a challenging situation. This is another great advantage of MATLAB. MATLAB provides you the tools to deploy your compute system on all the different stages of this process. On the hardware level, you can use code generation tools such as embedded coder, HDL coder, and GPU coder in order to generate C code, HDL code, and CUDA code that will eventually be deployed into your edge systems, field FPGAs and DSPs, or GPUs. On the other side of the process, you can scale up your computation and your algorithms to the infrastructure using compilation tools, which allow you to deploy your work and provide access for individuals, work groups, or enterprise through tools like Compiler SDK, and MATLAB Production Server. Overall, MATLAB can seamlessly integrate with different data sources coming from databases, clouds, or big data repositories. And it is also able to publish data into different formats, whether you are using streaming platforms, OT platforms, or dashboards. You can also benefit from various cloud services in order to scale up your development, whether it is for training or for deployment. The final section of the pillars of pragmatic digital transformation is the use of agile development workflows. Historically, engineers used a variety of approaches in their workflows. This started with things like the waterfall method, where development process is simple and ongoing. In reality, this doesn't really match well to the actual situation. This was improved using the spiral approach, where the developer loops through different phases until he or she reaches the desired deployment. Nowadays, DevOps is one of the popular methodologies that revolves around the continuous plan, design, build, and monitor loop. DevOps and Agile work in tandem since they complement each other. Under a DevOps model, development and operation teams are no longer siloed, but merged into a single team where the engineers work across the entire application lifecycle. These teams use practices and the technology tooling which helps them operate and evolve applications quickly and reliably. Model-based design marries well into the DevOps workflow and can help you in each and every step of the process. You would ideally start with model-based system engineering tools that help you in the planning stage by providing a framework to build your high-level design, architecture models, and to collect your system requirements. You can use MATLAB and Simulink to simulate your systems and subsystems across multiple domains, including physical domain simulation. Throughout this process, you can use source control tools like GitHub and Subversion for version control. Once you are satisfied with your simulations, you can generate code that will eventually go into field devices using code tools such as Embedded Coder, HDL Coder, or GPU Coder. These will allow you, as we mentioned previously, to generate C code for edge systems and microcontrollers, HDL code for FPGAs, and CUDA code for GPUs. In a model-based system engineering workflow, testing, verification, and validation can happen earlier in the cycle at the simulation level, at the high-level architecture level, and eventually at the code level. This allows you to capture errors in earlier stages and have a more efficient development process. Within this cycle, tools like Jenkins, Travis, Azure Pipeline can be used to ensure continuous integration and continuous delivery. As we go to the deployment stage, we can use generated code and directly deploy it into embedded and edge systems. Or we can use things like Dockers and Kubernetes to deploy into IT and OT systems. Logging and dashboard tools like Tableau and Click can integrate with MathWorks tools to facilitate the data logging and monitoring stage. Throughout the different stages of the development DevOps workflow, you can benefit from cloud services like AWS and Azure to scale your development through ready-made integration workflows. This completes the DevOps loop, and you can see how you can use the same platform in order to go from plan to release in a continuous cycle using MATLAB and Simulink environment. If you are dealing with a data-centric application where you start with data, the process remains very similar. Although you might come across more specialized platforms for big data, OT, and data streaming, which can vary from one industry to the other. The process itself remains unchanged, but you might come across tools such as PI Aussisoft, which is very common in the oil and gas industry. Or you can be using big data analytics platforms such as Cloudera and Hadoop. These will integrate as well with the model-based system engineering and model-based design DevOps cycle that we mentioned previously, and we have a lot of ready-made resources that can help you get started if you're interested in implementing that. So how to start? Based on this presentation, we can come up with different conclusions. Digital transformation is not something that will happen in a day. It is something that will take years. It will require changes throughout the entire life cycle of development. It includes developing the team's skill set and capabilities. It includes tighter integration between different teams and work groups. Model-based design is essential for digital transformation. It is not possible to have one without the other. So how to get started? This is something that we would be very happy to hear from you and to help you with. If your company has a vision for digital transformation and you are unsure where to start, we would love to help you with that. Our help can start from helping you understand how the model-based design and model-based system engineering workflow can fit within your organization, how you can use these workflows to implement your digital transformation vision. And this help can extend to various aspects of the development, whether it is the process assessment or it is consultancy and advisory services. We have engineers who are happy to talk to your engineers to understand their workflow and to assist them in their studies and their research about this topic. So please feel free to contact us if you would like our help in anything related to your efforts for digital transformation or for your effort to implement model-based design and model-based system engineering into your existing setups. You can use these contact points to communicate with us, and we will be happy to support you in that. So this concludes our presentation. We have time to go through some questions if you have them. So if you have any question, please feel free to type it on the chat window or to open your mic and mention it directly. So we had a question on the chat asking about the recording. Yes, the recording will be available and we will share it with everybody later today. So we have a question on the chat. Can you give example of the usage of FPGA in the oil and gas industry? So FPGAs are usually used when it comes to applications such as signal processing, where you would like to uh, analyze and process signals in real time. This can happen at the level where you are capturing, for example, vibration data from machines on the field, and you want to use that to take hard real-time decisions. FPGAs usually have a limited processing capability due to the availability of space, and most of the time it is mainly used for time critical and hard real-time applications. So you would not see FPGAs on things related to advanced algorithms or AI algorithms and so on. It is more used on the part of the workflow where you are analyzing a signal, you need to come with a decision on the fly and give an output or a control command to a device. So you might come across it for analyzing signals on the device level and controlling the device by extracting some output of that signal. This is the most used in the oil and gas industry. Having said that, FPGAs are more common when it comes to communication systems because they handle a lot of the communication algorithms on real time. So this is a more common application for FPGA in the industry. Anybody has any other questions? We still have some minutes left, so if anybody has any question, please feel free to post it on the chat.
Yes, I have another question. Sorry.
Yes, please go ahead.
For simulation part, so for example, most of the machine is like black box for us. How we can how we can simulate it in MATLAB, for example. If you have a pump or turbine, how we can simulate these things? Is there is any like mathematical presentation for it that will be provided by manufacturer, and most of them they are con- confi- consider it is like confidential information. So how we can simulate it?
Yes, exactly. That's actually a very good question. To answer this question, one option is, as you mentioned, some manufacturers do have schematic drawings of the pump internally. It doesn't have to be a simulated model, but most of them they have some schematic drawing showing the internal build of the machine. If you have this schematic of the machine, even if it is on paper, you can use MATLAB and Simulink to replicate the different components of the machine. So this is one, if the manufacturer is not providing the simulation model, which is the case most of the times, you can try to build it yourself by building the different components that go into this device inside MATLAB and Simulink. However, having said that, for some parts of the machine which remain as a black box, and you cannot have visibility of how they are built internally, you can benefit from different tools that go hand in hand in Simulink to do that. For example, let's say you have a component that you don't know how the mathematical equation is for it. You can use things like system identification, where you can try to give it different inputs and checking the different outputs, and then use MATLAB and Simulink to derive the equation. So this is some kind of reverse engineering that happens inside the software, and it will give you an approximation of the equation of this component or this piece of hardware. Uh, Another thing that to take into consideration is many of the equipment have a standard way of manufacturing. So if we look at a pump or a compressor and so on, their internal build is very similar to one another. The components can change, the level of manufacturing can change, but the basic components are the same. So you can use physical component modeling inside Simulink to try to replicate the behavior of this machine.
Okay, it's clear. But now we're coming to this system identification tool. So I have been used MATLAB before, and when it's come to dealing with the real-time systems, we use the Laplace equations. So do we need to transfer these like real-time application to Laplace, or no need? So this tool will take care about the inputs as in time.
Exactly. So here, this is one of the advantage of the flexibility of MATLAB. You have the option to convert to Laplace, but this is not something obligatory. So in this example, we are not doing any kind of these transformation. We are actually designing the system using physical components. And Simulink will take this conversion from the physical component itself into the time domain so that it is integrated with the rest of the system inside Simulink. So here you are not actually building a transfer function or any kind of approximation of the device. You are actually building the physics of the device inside the tool, and then MATLAB will take care of these Simulink, sorry, will take care of these conversions in its high level and be able to integrate it with the different aspects of your system.
Okay, it's clear. Thank you, brother.
You're most welcome. So any other questions?
Yes, good morning. This is Mohamed Jahdari from Bet Huraba. I have one question regarding the MATLAB simulation. Is it like the HISIS simulator that it's a steady state, or it can be dynamic simulation?
Yes, it can be dynamic simulation. The main advantage of Simulink is that it supports dynamic behavior. So it is not just a steady state system, it can also handle the dynamics part.
Okay, thanks so much.
Any other questions from anyone? As my colleague mentioned on the chat, so if anyone is interested on organizing a follow-up call on this presentation, if you would like to know any specific information about something that we mentioned, it doesn't have to cover the entire thing. If your interest is mainly in a specific portion, for example, the AI part, the modeling part, the simulation part, etc., we'd be happy to communicate with you to have a more in-depth discussion on the topic. In this presentation, we try to keep it high level to highlight the different aspects that go into the efforts to achieve digital transformation at a company, but we'd be happy to spend more time about any specific section if you are interested in that. So with that, I would like to thank you all for your time. As mentioned, feel free to reach out for us for any technical or sales inquiries if you would like to know more about any specific topic. This recording will be shared. If you're interested about any specific materials that we showed during the presentation, we would be also happy to share videos and more detailed technical information about these sections. So feel free to reach us. And with that, I would like to wish you all a very nice afternoon, and please stay in touch. Thank you very much for your time and have a nice day.